Have you ever wondered how an AI in a video game seems to know the perfect route to its goal? Or how a robot can figure out the most efficient way to do a task? Well, a lot of that magic comes down to a core idea called value iteration. It's basically the method an agent uses to build the absolute best plan to win. And today, we're going to break down exactly how it works. So, here is our game plan. First, we'll set the stage and look at the actual problem we're trying to solve. Then, we'll use a super simple treasure map analogy to make it all make sense. After that, we'll see how the values on that map spread out, how we use that finished map to find our way, and finally, we'll boil it all down to one single big idea you can take with you. All right, let's kick things off with the fundamental challenge. In reinforcement learning, good enough isn't really the goal. We're hunting for the absolute best path. So that brings up the big question, right? How does an agent actually figure out the best possible plan? It's not always obvious, because the best move right now might not lead to the best outcome down the road. It requires a bit of foresight, a way to think ahead about delayed rewards. Now, this best plan has a fancy name in the field, the optimal policy. You'll often see it written as Pi-star. Just think of it as the ultimate playbook. It's a complete guide that tells the agent the single best action to take from any state it could possibly be in, all to get the most reward in the long run. Finding this policy, well, that's the whole point. Okay, optimal policy can sound a little abstract, so let's ground this whole idea in something we can all picture, a simple treasure hunting game. Picture this. We have a little agent on a grid. Somewhere on this grid, there's a treasure chest. Let's say it's worth a big reward, like 10 points. But there are also some walls our agent can't move through. The goal is pretty straightforward. Get to the treasure. And this is the really important part. We don't just want to find one path from one starting point. Our real goal is to create a complete treasure map, a map that tells our agent the best move to make no matter which square it's on. This map is what we technically call a value function. So how do we actually build this perfect map? Well, we do it step by step, or you could say iteratively. First, we need a way to score every single square on the grid. We'll call this score the state value. You can think of it as the treasure potential of that spot. A high value means, hey, you're getting warm, the treasure's nearby. A low value means you're cold, you're far away. Our entire mission is to figure out this value for every spot on the map. And the way we do that is with a really simple loop. First, we start completely clueless. We just set the value of every single square to 0. Then the process begins. For each square, one by one, we look at its neighbors. We ask, which of my neighbors has the highest value right now? And then we update our own value based on that best neighbor. We do that for one square, then the next, until we've swept across the entire grid. And here's the key. Once we finish the sweep, we just start over and do it all again. Let's actually see this happen. Here's our map at iteration 0, the very beginning. It's a total blank slate. Every square is worth 0 because our agent knows nothing. The only things we know for sure are that the treasure, T, is worth 10 points, and the W is a wall we can't go through. Now, that simple update rule we use has a fancy name, the Bellman optimality equation, but don't let the name intimidate you. The idea is incredibly simple. It just says that the value of where you are now is determined by the best place you could possibly go next. It's all about looking just one step ahead. So, after our first full sweep across the grid, look what happens. The value has started to spread out from the treasure like a ripple in a pond. The squares right next to the treasure now have a value of 9. You might be wondering, wait, why 9 and not 10? Well, we often use something called a discount factor. It just means that rewards you get in the future are a tiny bit less valuable than rewards you get right now. Think of it as a small cost for each step you take. Okay, let's fast forward a few more iterations. Now the map is really starting to take shape. You can see this beautiful gradient of values spreading all the way across the grid, flowing around that wall. The numbers get bigger and bigger the closer you get to the treasure. Our map is now full of really useful information. So we've run this process over and over. We've filled our map with all these numbers. What was the point of all that? Well, this is where it all pays off. You see, after we run this loop enough times, something really important happens. The values stop changing. The numbers on the map stabilize, and they just don't get any better. They've converged. And at that exact moment, we know we're done. We have officially found the optimal value function. Our treasure map is complete. And here is the aha moment. With this finished map, what was once a complex planning problem becomes incredibly simple. From any square on the board, the best thing to do is just move to the neighboring square with the highest value. You just follow the numbers uphill. And this set of arrows, this guide for every single square, that is the optimal policy we were looking for from the very beginning. You know, what's so elegant about this is that it's doing two things at once. As the experts say, each sweep is both evaluating how good the current map is, and at the same time, it's improving it. It's this cycle of evaluate, improve, all in one motion, until it can't get any better.
So let's zoom out. If you're going to remember just one thing from all of this, what should it be?
It's this. Value iteration takes a really complex, long-term planning problem and solves it by repeatedly applying a super simple local rule. You just keep applying that simple rule over and over again, and eventually, the perfect global solution just emerges.
This whole process is incredibly powerful. But you might have noticed it relies on a pretty big assumption. We knew the whole map and all the rules before we even started. So that leaves us with a really interesting question. What happens when the agent doesn't know the map? What if it has to learn as it goes, just by exploring? Well, that's a fantastic question and one we'll dive into next time. Thanks for joining me.